Hi, this is Jeff Coronado on behalf of JCSE, and this is Bridging the Gap. So this is an ongoing series of structural engineering design tutorials that we have here at JCSE. We call them Bridging the Gap because the idea is that they're useful. Primarily, they are intended for the younger structural engineer, either still in college and looking to get a head start on understanding things from a practical perspective. Or engineers who've been working for maybe a couple years who are still looking to make that transition to fully understand how things are done in practice versus where their education at school left off, and hence why we call it Bridging the Gap. Hopefully you'll find these tutorials useful to you. The title of this particular session is How to Calculate the Lag Bolt Capacity. It's in particular, it's for a situation where we have an unreinforced masonry chimney. So what one of our young engineers here is asking is about shear planes in their lag bolts. Okay, so get all you can out of this tutorial. It's kind of a word to the wise, if you will. Sometimes younger engineers want to skip around a little bit, kind of just get to their answer. And that's not really the purpose here. The purpose of these tutorials is to kind of empower you to think as a structural engineer, so that the sooner that you're able to kind of bridge this gap, if you will, the sooner you'll be able to see things as a structural engineer and then be able to resolve the issues on your own without outside assistance. So bear through the entire tutorial, absorb the lessons, take notes if you need to. It's one of those things that if you do it right, you only need to do it once. Let's jump into the roof framing here. So what we've got is, let's see. We've got this line here is the edge of a roof. So we've got a roof edge. Here is our, no, don't want to do that. So here is our chimney, all right? So we're looking at this in plan view. There's our chimney. All of the red hidden lines are primarily our walls that are below the roof. So our ceiling, therefore, our ceiling would be the area that's bounded by, oh, didn't know I was doing circles. Right? It's this area bounded by this green line. So, so all of this area is our ceiling, all right? So again, the red line is pointing to the roof edge, while the green line, the interior of the green line is where there's ceiling, and the green line that I did on the perimeter, those are exterior walls. Now, what we're going to discuss here is something that is a seismic effect. So primarily a seismic effect. So the greater the seismic region that you are doing a design in, the more that this will be an issue for you. However, one of the things that we need to take into account is in an earthquake, that chimney is going to want to pull away from the structure. Now, you might ask yourself, why? Why would it pull away? And let's cover that in another Bridging the Gap session. Let's not get bogged down with that too much, but it has to do with different periods of vibration between the chimney and in this case, this is a wood-framed structure. But the chimney is going to want at times to pull away from that structure. So what we need to do is to anchor back the chimney back into the structure. We need to do that at the roof level, and we need to do it at any floor If there's like if this is a 2-story, 3-story structure, we need to do it at the floors. And just below the roof, if we have a separate ceiling, we need to do it at the ceiling level as well. In this session, what we're covering is that ceiling condition. Now, before we do this, we need to understand where our shear walls are at. Well, in looking at this, it's pretty safe to say we're going to have, don't want to do that. It's pretty safe to say we're going to have a shear wall here. So this is, again, for an earthquake that is going, that's in the vertical direction on the page here. So we need vertical shear walls that are oriented in the vertical direction, parallel to the direction of the earthquake, to resist it. So we've got a shear wall where I've shown you the black line. I'm not really sure if we have another shear wall here or if we have another shear wall here. And it really doesn't matter for purposes of this tutorial. So let's just assume the shear walls are as located by the black lines. Now let's start thinking about our ceiling between those shear walls. So start thinking about our ceiling between those shear walls. Let's look at the yellow shaded area here. So what we have here is a bit of a diaphragm, right? A bit of a diaphragm assembly, if you will. It's not a full-blown diaphragm. It's not a real diaphragm, but I think we can visualize it that way, right? The yellow area is a diaphragm. The red arrow represents the earthquake force that's going in the upward direction here on the screen. The yellow area, which is the diaphragm, spans between those shear walls, and it'll resist. It'll transfer the load from the earthquake into the shear walls. If we look at this even more simplistically, I guess, just to be able to model it and be able to analyze this, we can think of this as literally a simply supported beam, right? It's a simply supported beam. It's supported at each end by the shear walls, and the force that acts on the beam is the earthquake force generated at the chimney. Now remember, this diaphragm is nothing more than our ceiling, right? So good chance that this is just drywall. This is just gypsum wallboard. However, there are two things that are going to govern the dimension for this diaphragm. One thing that we would need to take into account is we want to make sure that we can actually transfer the force. We actually want to transfer the force from the chimney into our diaphragm. So we kind of have to embed that, if you will. It's kind of like the concept of embedment, right, or development length. And if you're not clear on any, by the way, if you're not clear on any of the things that we're saying here, that we're discussing, you can search other tutorials on our channel, and you might find them covered there, or leave us a note at the end of this tutorial and ask, and we'll try to point you in the right direction. But this is a matter for another session in Bridging the Gap. But you do need to be cognizant of the depth needed to transfer the force in from the chimney. And then the other thing that you need to be aware of is, let me just do that. You need to have enough length, enough depth to the diaphragm, to this little subassembly diaphragm that we're doing, to transfer the force out of the diaphragm and into the shear wall. Now, with this in mind, let's cut a section right through here so that we can look and see how we're pulling the force from the chimney back into this gypsum wallboard diaphragm, if you will, to make that force transfer. All right, so let me clear the screen here and let me scroll down. Okay, that gets us to this. Now remember, that was the section from up here, right? The chimney's to the right. So let's take a look at what we've got going on here. Where's my pointer here? Oh, you know what? Before I do this, let's go back up here again, just for sake of illustration. Perhaps the one thing that I didn't state is, in this case, the ceiling joists are going from left to right, okay? So that's a ceiling joist, this is a ceiling joist. The ceiling framing is going left to right across here. Again, anything that you don't understand that we're talking about, by all means, leave a note at the end and we'll try to point you in the right direction. Okay, so with that in mind, now let's again scroll down. So here, this is kind of a blow up of what we've got in that section that we talked about doing. So what we've got here is, here's the ceiling, all right? There's our drywall. In red, I'm gonna show you the ceiling joists. Okay, so these are ceiling joists. In yellow, I'm gonna use to point to blocking that we are placing between the ceiling joists. Again, if the concept of blocking isn't clear to you, go ahead and leave a note and we'll try to take care of that. And then we've got these lag bolts. We've got these lag bolts. Oops, sorry. So we've got these lag bolts here, but now, interesting, look, we've got two things, and so I'm going to show you maybe in magenta. We've got two things. We've got two things. It looks like we have material right there, and it looks like we have material right here, right? It's almost like there's two additional materials placed on top of the ceiling joists. And that's what's shown with the magenta arrows. So in this case, I'm going to hazard to guess, that this sheathing, go to a straight line here. This sheathing here, this drywall across the bottom of the ceiling joist, that's just the ceiling wasn't adequate to transfer the forces that we needed to transfer through that little diaphragm assembly. Remember, we talked about a minute or two ago about needing sufficient depth of the diaphragm assembly to be able to, one, embed the force from the chimney into the diaphragm, and we needed enough diaphragm depth to also transfer the forces out of the diaphragm assembly and into the shear wall. However, in this case, what we encountered was we weren't able to transfer those forces through what we consider to be a reasonable length of diaphragm. So what we did was add, and it looks like we may have added two materials. Let's maybe use terminology like additional sheathing. We needed to place some additional sheathing in only that area of diaphragm that we're trying to transfer the forces through, not the entire ceiling, but only the area of diaphragm that we're creating to transfer these forces. We placed additional sheathing over the ceiling joist to give us the strength that we needed for that small diaphragm assembly. It looks like we may have even added 2 layers. We could have used plywood. We could have used drywall. Maybe we're using 2 layers of drywall. Not really sure. I think that some of that probably needs to be covered, or should have been covered in another Bridging the Gap. And again, if that idea of adding an additional layer of sheathing isn't clear to you, leave a note and we'll try to take care of that, or at least point you in the right direction to another Bridging the Gap session. But we do have 2 layers here. Not real critical to understand that for the purposes of the transfer from the lag bolts. So a pretty nifty solution here to strengthen the diaphragm in that local area. And again, we're using the term diaphragm pretty loosely because it's not really a diaphragm. It's just kind of acting. It's an assembly that's acting as a diaphragm so that we can resolve the forces induced by the chimney. It's not really a diaphragm, but pretty nifty to strengthen this diaphragm assembly, if you will, to be able to have the strength to transfer those forces. All right, so let me clear this. The one thing that that we need to be aware of, though, when we're doing this, is if you are going to add this material or this material, keep in mind that that potentially affects then other details. So that's one of the lessons that you need to learn, right? Kind of be cognizant of not only the immediate picture, but be cognizant of the bigger picture. Be cognizant of how that change that you're making is going to potentially affect other sections, other details. You then need to address that, make the changes there. A little bit of what we talked about, which we're not going to cover in this session, but remember we said that we needed to transfer the load out of this diaphragm assembly and into the shear wall. And now you're introducing this new material. So the new material needs to be, there needs to be a shear transfer between this new material, this new sheathing, if you will, and those shear walls. You need to clearly specify what this assembly is, right? You need to be clear on, is this, what thickness this is. You need to be clear, the contractor certainly needs to be clear on how far this is spanning, this material is spanning, whether you're reflecting that in the plan view or in sections, it needs to be clear to them. So how far does it span over? I mean, yes, you understand as the engineer, you understand it needs to span between the shear walls, but is that going to be clear to the contractor? So you need to be clear on the width of this material, the depth, right? Remember, this is kind of an artificial or an arbitrary addition that we're doing. So is the depth of this new sheathing 2 feet, 10 feet? You know, what do you need to develop your forces? And then you need to show that to the contractor. So how wide is this material? How long is it? The thickness, right? If this is plywood, drywall, and what thickness it is, and yeah, what material is it? So so if you're going to do this, you do need to be clear about the materials. You know what? I just realized something. I take this back. We are not adding two separate materials here. So let me get rid of, no, I didn't want to get rid of that one. That's okay. So here's what we've got going on, guys. This is the material that we're adding. This is the material that we're adding to the sheathing we're adding to bolster this diaphragm assembly. However, this, what I'm showing you in black here, that's the steel strap. That's the part of the steel assembly, the steel strap that is anchoring the chimney, connected to the chimney and pulling the force back into the ceiling framing. So this here is a steel strap. All right, so only the layer below that is the sheathing that we're adding to bolster the diaphragm. All right, so with that, let me clear the screen. And let's see what else we've got here that we need to cover. So vigilant about changes to other details. Yes, we've covered that. Okay, the lag bolts, shear transfer from the steel plate. Okay, right, from the steel plate to the gypsum wallboard. Okay, so yes, indeed, it does look like we are bolstering our diaphragm assembly by adding another layer of gypsum wallboard. So now we have to visualize what these lag bolts are doing. And by the way, if the concept of a lag bolt's not clear to you, let us know. We'll point you in the right direction, okay? But here's what these lag bolts are doing. So we have a force, let's say this, let's look at this, let's look at this lag bolt. Okay, so we've got the steel strap pulls the bolt to the right. So first we need to make a transfer. We need to make a transfer through the lag bolt into this layer of drywall that we've added to bolster our shear wall assembly. But then we also need to transfer shear force into into the block, into this block right here, this block, so that ultimately this load can go out of the block, and into the layer of drywall. That's actually the ceiling. Yeah, that's actually the ceiling. Okay, so the force that's induced in the lag bolt is in the steel strap, right? So the steel strap is pulling the lag bolt to the right. So some of that force needs to go out into the drywall that's above the ceiling joist, and that's the blue arrow. Some of the force gets resolved there. So that's one shear plane that we have. The rest of the force needs to go into the block. So that's another shear plane for the lag bolt, where it transfers the force out into the block. And then that force needs to migrate through the block and out the drywall on the bottom side. So now we have to size these bolts, these lag bolts. Now, the common mistake that's made by some engineers is they will look at it like this. They will say, we've got a wood block down here and a steel strap here, and therefore I am transferring force between this steel strap through the bolt and into the block. Now the problem with that is that then we're saying there's a force acting here, and then there is a force acting here, right? So is there a problem there? Think about it for a second. And the answer is yes, there's a problem, because literally what you're asking this bolt to do then, didn't mean to do that, sorry. So what you're asking this bolt to do is to bend. If you exaggerate this, that bolt is going to be bending from where the force is applied on the steel, at the steel plate, and resisted by the blocking, right? There's a lever arm here. There's a moment induced on the bolt. We don't want that, right? Bolts aren't rated for flexure. We can only transfer shear. So we need to keep the force transfer at a shear plane, not a shear area, if you will. So so we don't have a load transfer from the steel plate into the blocking. That is not what we're doing. Instead, the way you need to think of this is is we've got a shear transfer that occurs on the plane between the steel plate and the gypsum wallboard that was added to the assembly. And we've got a second shear plane between the gypsum wallboard and the blocking. We've got two shear planes that we need to take into account in sizing our bolt. So let me see if I can now scroll up screen here. Okay, so right, we have two conditions for the lag bolts. So we've got the shear plane illustrated by the red line segment. That's a shear transfer between the steel plate and the drywall. And we've got a second shear plane created between the drywall and the blocking. So now I need to come up with this design. And I means you, right? You need to come up with this design. How do you size the bolt for these two shear planes? Well, it wouldn't take a whole lot, I think, a whole lot of common sense to think if I'm transferring the force between a steel plate and a piece of drywall, and I'm also transferring through the same bolt and the same drywall force into a block, into a wood block, the weak plane there is going to be the drywall to the block. Now, maybe you might need to think about the steel plate and so forth, but I think if you think about it and visualize it, I think you can make peace with the fact that if this lag bolt is strong enough to transfer force between the drywall and the blocking, then it'll likewise be strong enough to transfer the force between the steel plate and that drywall. So in essence, really, it's the drywall that becomes the weak link here, right? So you need to provide a lag bolt that, based on the capacity, based on the capacity of this shear plane between the drywall and the blocking. So it's not based on the capacity of a bolt connecting a steel plate and blocking. It's a bolt that is based on the capacity, based on the capacity of a bolt connecting drywall to your blocking. Okay, so with that, let's scroll up. The embedment consideration, yes. Another thing that we need to consider here is this embedment depth of the lag into the block, right? So here, just graphically, it looks like the embedment for these lag bolts are probably in excess of half of the depth of the ceiling joist. Now remember, the force that you're transferring is from drywall to the block. So it is hard to visualize that much force is being transferred into the block. Now, if it was the steel plate, maybe you would need to engage all of this depth of blocking, right? If you were transferring the force from the steel plate, but you're not. Remember that the transfer across this plane is between the drywall and the block. And that's what's going to dictate then how much you need to embed the lag bolt into the block. So hard to visualize that you would need this much embedment, but again, that's a matter for another tutorial in bridging the gap, is how to determine those embedment depths. If you have a question on that, let us know. We'll try to point you in the right direction. Okay, so let me clear the screen here. And that's it. So that completes this tutorial. Sure would appreciate you giving us a thumbs up if it was helpful to you. Any comments or suggestions, please, by all means, leave them, and we'll try to incorporate that as we go along. If this was helpful to you, please consider subscribing to our channel here at JCSE, and that way you can subscribe and you'll be notified of new tutorials as they come out. Okay, real good, guys.